So in the concept of shared memory and message passing, we have seen that in the shared memory concept, the memory is shared between two processes. So the address space of one process will be, so inside the address space of one process, the shared memory address also be there, as well as for another process also. So it will be a overlapping way of uh, address space, and based on that they can communicate with each other. So one process is putting some data or writing something on the shared memory. Another process will read the data from the shared memory. In that way it works. In the message passing concept, will not have the sharing resources. Instead we have the kernel. So kernel will send whatever message we have to the kernel, and from the kernel a process will take the message. So message passing generally work in a distributed environment where we have distributed systems, and they can communicate with each other through the concept of IP address and the port number. And based on that they used to communicate. After that, we have seen one example of producer and consumer. So what happened in the producer consumer problem is, producer is producing the data and consumer should consume the data. So this is one program that we have seen in the last class, that how this resources will be shared. So we have many resources that can share, right? So what are the resources that can share? So we can share the resources like CPU, we can share the resources like memory, we can share the resources like variable. Actually not the CPU. CPU is, let's say we assume that we have only one CPU, so CPU will not be here. Instead we have the variable. Either we can share the variable or the memory, or some sort of code, programming codes we can share in between two processes, or we can share some hardwares, like we can share printers, we can share some hardware, we can share between processes. Let's say we have printer, we have a scanner. Okay, the networking switches, all those things, the network part also can be used as a shared. So let's assume that we have a producer which is always producing the data, and we have a consumer which is always consuming the data, and they will have a shared resource which is a buffer. So in between a producer and consumer process, we have a buffer, and responsibility of the producer is to produce that produce whatever it want to produce and put into the buffer, and consumer will take those particular data. So here we have a counter. Counter will tell us about how much data we have. So depend upon the buffer size. So let's say the buffer size is, let's say, 5. So we can put only up to 5 data. If it is equal to, means the counter and the buffer size, it is equal, it means that the buffer is full. If buffer is full, then producer cannot produce the data. Why? Because it doesn't have the place to put the data, right? At the same time, if counter is 0, it means that there is nothing into the buffer. So here also consumer cannot do anything. So it will go in a loop. So it is a while, and then semicolon means if it will be this condition will be satisfied, so it will be go on a loop. Now what producer is doing is, if the buffer is not full, then buffer dot in, whatever the value of in is, will be putting the next value or the next whatever value it want to put into the buffer, and it will increase the in value. So let's say initially the in value is, let's say 1, so it will put the value into that particular position, or it will start with 0, so it will put the value on the particular position and make it in equal to 1, right? So in that way, what will happen is, whenever we find out that counter value which we have initiated with 0 will be equal to the buffer size, it will be, what it will do is, it will be saying that the buffer is full and the producer cannot produce the further data. In the same way, if we have a consumer, and if it is not 0, means if the buffer is not empty, means some data is there. So what it will do is, the consumer will consume the data, and it will just make it out plus 1. So up to the buffer size it will go and consume the data, and it will make it counter minus minus. It means that, let's say instead of 5 we have 2 data available. So in the first way, because counter is not 0, the value will be consumed, and out is there. Out will be, let's say, initialized with 0, so it will go to the 0th position, consume the data, increase the value, come here, consume the data, increase, and then what it will do is, you can see that counter value is also reduced. So once the counter, here what we have, the counter value is 2. Once it will do one consumption, it will be 1. It will do another consumption, it will be 0. Once the counter value will be 0, it cannot do anything, and it will go into a infinite loop. So this is how a producer consumer is. Now there are some issues related to producer consumer problem, and that problem we are going to see today and try to find out the solution for that. So let's see here, we have two type of buffer that we can use. We can use unbounded buffer, or we can use bounded buffer. In this particular case, the example that we have just seen about the producer consumer, here we are talking about bounded buffer. We may have unbounded buffer, in which buffer size is not at all a constraint. So producer can produce. So producer will not going to stop, but consumer will stop when there is no value into the buffer. Now, when we talk about bounded buffer, so we have some bound into the buffer, and we know that these much of data only a buffer can accommodate. So producer will also has to wait if data will be full here, and consumer also has to wait if there is no data. So in both the cases, a producer has to wait as well as consumer has to wait in a bounded buffer. But in an unbounded buffer, both is producing, producer is producing, and it is not going to wait, but consumer need to wait. Now in this case, what will happen is, if we have unbounded buffer, so in this case, producer keep on producing the values, and consumer will never get chance to be consumed. So that may be the chance. That's why this unbounded buffer scenario is not at all good for the efficiency of the operating system or efficiency of the whole system. So we should have the bounded buffer. Now, one problem we have solved, that we need the bounded buffer, which will make some sort of constraint so that both the processes can run. Now let's talk about another problem that we can see in the producer consumer scenario. Let's talk about race condition. Okay, so for that I'll take one example. Let's say we have two processes. Let's say we have process P1 and process P2. Okay, let's assume that we have a variable called shared and a variable called X. Now here let's assume that we have a variable which is shared among both processes, which is P1 and P2 is shared variable. Okay. Now assume that we have some value in the shared previously. Let's say the value that is there in the shared variable is 5. Okay. Now to taking the value as 5, let's execute process 1 first. So if we have a process 1 and the shared value is, let's say, 5, X value will be 5. Now X plus plus means X value will be 6. Now after that it will go to the sleep mode. Sleep mode means it will come to the ready state. Now because we are talking about, let's say we have only one CPU and we know the property of the CPU. If it find out that a process want to go out from that particular CPU, it will take immediately, it will ask the scheduler to arrange another process. So once P1 is in the sleep of, let's say, 1 second, CPU will ask another process. Let's say P2 is there in the ready state, so P2 will be coming here, and now it will take the shared value. Shared value is right now 5, and Y value will be 5. Y minus minus means Y value will be 4 right now. So here X value is 6 and here Y value is 4. Now after that it will go to the sleep, means it will go from let's say it will not do anything and it will go to the sleep, means after that whatever instruction is, for that it will take 1 second of pause. At that particular time, let's say this 1 second is over and P1 will be get into the CPU. Now once the P1 will be get into the CPU, the next instruction is shared equal to X. Now the shared value right now will become 6. Why 6? Because it will take the value of X. Now after that, let's say the program P1 has been executed. Now after that, P2 will come, and because we know that in the context switching, we store the state of all the processes, and while storing the states, we also store the program counter. Program counter will tell what is the next instruction is going to execute. So we are talking about next instruction in the program that is going to execute. So we know that after the sleep, the next instruction is shared equal to Y. When I'll do that, this shared variable will be rewritten as 4. Now, what is the output of the shared variable right now? It is 4. Is it correct? Now the answer is it is not at all correct. If we have an initial value 5, once we do addition, after that we do subtraction, the value will be 5 only. right? So 5 is the correct answer. Now, if we execute, let's say P2 first, so one will do it for another serial way of execution. Let's say we'll start with P2. Now, if we'll start with P2, we know that the value of this particular shared variable is 5. So to take 5 as the value in the shared variable, the y value will be 5, and it will be 5 minus minus. Again, it will be 4. Now after that, it will go to the sleep mode. Assume that the initial value is 5. It will go to the sleep mode, and then a CPU will be asked for another process. So this process will be there. Now the shared value of this process, it will be 5 equal to, x equal to 5. It will be x plus plus. Now the x value will be 6. Again, it will go to the sleep mode. The P2 is going to execute. Y value will be given to shared value. So y value is 4. And then once this will be over, P1 will come. P1 will have one instruction left. This will execute, and the shared value will be 6 right now. Now, in the previous case, the output was 4, and this case, the output is 6. In both the cases, it is not correct, right? So that thing is called race condition. That problem, that condition that we have just seen is called race condition. The meaning is both the processes they want to execute execute their instruction, but because of the shared variable, because of this shared variable, we cannot do the serial scheduling. Once we do the serial scheduling, we find out that there are some problem that will be occurring, and because of that, my output is not at all correct. Either I'll execute P1 first and then P2, or I'll execute P2 first and then P1. Both the cases, the output is not at all correct. Now, if the output is not at all correct, then what? So that particular condition is called race condition, and this particular is the problem related to the this particular problem is actually the problem related to this inter-process communication, when two processes want to communicate with each other. Okay, now let's talk about this example that has been said. Now this is the example of the previous producer-consumer problem, where it has taken as in the counter value. So the counter value is there, counter plus plus and counter minus minus. It is telling about that particular counter. What it is telling that how the counter plus plus is going to work. So the counter value will be given to the register will increase, and then register value given to the counter. Now the same thing will happening here in the counter minus minus, counter value given to the register 2 will be -1, and then register 2 value will be given to the counter. Now you just assume that the initial counter value is 5, and while executing, we are executing in this way. Let's say we are executing 2 instruction of the program. So the register 1 value is 6, and then this program has been preempted. So we can preempt any program at any time, okay? And then we'll execute these 2 instructions. Once we'll execute these 2 instructions, the register value is 4. And then we execute this instruction, so the counter value will be 6. And once we'll execute this instruction, the counter value will be 4. In this particular case, the case of what we have seen is the same. Here also, the problem occur because we haven't executed all the instruction at once. Once we'll execute all the instruction at once, we can actually do the, we'll get the correct answer. So that particular problem that has been faced, and that thing is happening because of our operating system that we are using. in a preemption way, or the preemptive scheduling that we are using, in which any process can come into the CPU and can take out the already executed CPU from that particular CPU. That thing is called preemption. And we know that if we have the higher priority process that will come, so we need to take out the process which is running right now, or in a round robin scheduling algorithm, if the time quantum is finished, then also at that particular time also we need to take out the process which are just running into the CPU. That part problem is called race condition problem. Now, how we can solve this race condition problem? We can solve this race condition problem using process synchronization. If both the process will be synchronized, which share the resources, then that particular problem could be solved. Another thing is there, the part of the code in a program, in a particular program, the part of the code in the program which is having some shared variable or shared code, that particular part is called critical section. This particular part is called critical section. Now, the serial scheduling of the program is possible if we doesn't have the serial schedule, the critical section. If we have the critical section, then we have to look for some other measures, or we have to take some other steps so that the inconsistency will not occur in the system. Here, shared resources that has been used is share, and this particular, you can see this particular part in the program is nothing but critical section, where the shared resources has been modified. This particular section is critical section in this particular example. So let's talk about critical section. What is the critical section? So the critical section is the part of the program where shared resources are accessed by various cooperative processes. So it says that it is a part of the program. So maybe you have a larger program, and there might be some part of the program where two cooperative processes are using the shared resources or doing some modification into the shared resources. That particular part is called critical section while we do inter-process communication. Now consider a system of n processes. We have some processes P1, P2, P3 up to Pn. Let's say we have open different applications. Each process has critical section segment of the code. What are those? So processes may be changing a common variable or updating table or writing files. So any of these can be possible. We have some common variable or common updating table or common file in which we are writing. When one process is in critical section, no other may be in this particular critical section. It says that if one process will be into that particular critical system and updating the value, so other process is not at all allowed to go into that particular critical section, because another process is in the critical section and modifying the data. If at the same time both the processes will come into the critical section, so there might be the inconsistency in the system. So this critical section problem is to design protocol to solve this. Each process must ask the permission to enter into the critical section. So before the critical section, we have an element called entry point or entry section. Okay. So this particular part that is there just before the critical section is called entry point. And then if it will satisfy the entry point or entry section condition, it will go to the critical section. And then once it will be out from the critical section, it will be executing the exit section code, and then we have some reminder of the code. So let's see, with the help of this example, let's assume that we have some program, and before, let's say, the entry section, we have some code. Now if a process want to enter into this critical section, and you assume that inside the critical section we have some code which is updating some variable or updating the table or updating the files, which is shared with other cooperative processes. So just before the critical section, we have an entry section. Entry section is some sort of condition that a process has to satisfy. Once a process satisfies that particular condition, it will go into the critical section. It will do whatever updation or whatever modification it has to do into the shared resource, and then it has to execute the exit section code. After executing the exit section code, with that particular process will allow to execute the remainder of the code. So you can see these are the code which are not critical or which are not shared. That's why these the order of execution of these is insignificant, but these should be the order. Means once a process want to execute into the critical section, it has to first satisfy the entry section conditions, and then only it will be allowed into the critical section, and then it has to execute the exit condition, and then only the remainder section is going to be executed. So this is how the critical section is, and we need the entry section, exit section in between the critical section. Let's see this example and try to understand. In this example, we have entry section. This is the entry section. Let's say we have a process Pi and we have a process Pj. Okay. So I'm just writing the code here. We'll come to the code later. Let's talk about an example. Is a similar example to that particular code where we have two processes. So we have process 0 and process 1. 0 and 1 is, you assume that is a process ID. Okay. Now here we have a continuous loop that will use here. So we have let's say while loop, and inside the loop I'm writing the code. In this we have a variable turn like this. If turn is not 0, then we are in the loop. If it is 0, then we'll come to the critical section. So we have critical section. So I'll write capital CS for the later example for the critical section. And then after that, the exit condition is, let's say, turn equal to 1. We have modified the value of turn. And then we have some remainder of the section. So we have some reminder section here. That's all. So this is P0. In the same way, I am writing another process. While 1, another condition while turn not equal to 1. Then it will go to the infinite loop. Then we have critical section. And then the value of turn will make it 0. This is my exit condition or exit section. And then we have the remainder section. So this is the critical section. This is the remainder section of the program. Now let's see this particular example. In this particular example, we have a loop. So this particular code is going to execute for infinite time, as well as this particular is going to execute for infinite time. Let's assume that the value of turn initially it is 0. If initially it is 0, then what will happen? Let's assume we have P0 that is coming into the ready state, and P0 will execute into the CPU. While turn not equal to 0, so that condition is satisfied? No, because it is equal to 0, that condition is not at all satisfied. If condition is not satisfied, we'll go to the critical section. If condition is satisfied, we will go into the infinite loop here, because it is a while loop and we have a semicolon here. So critical section is not the part of the while loop. It is outside the while loop. Now what will happen is, we are in the critical section and then we are doing turn equal to 1. We execute whatever is in the critical section, and then what we'll do is we'll do turn equal to 1. So right now turn is equal to 1. And then we'll execute the remainder section. Now what will happen when again P0 want to execute? Now if again P0 want to execute here, then it will go to the while loop. It will find out turn not equal to 0. Yes, it is satisfied because 1 is not equal to 0. It is satisfied, and P1 will be in the loop. So because P1 is in the loop, P0 is in the loop, P1 will be getting the chance for the further execution. Now once P1 will be executing, it will go for the condition, entry condition, which is while turn not equal to 1. So 1 not equal to 1, it is not satisfied. Then it will go to the critical section, execute the code in the critical section, and it will make it turn equal to 0. Once it will be turn equal to 0, P0 has a chance to execute. Why? Because P0 is here and all the time it is looking for the turn value. If turn value is not equal to 0. If turn value is 0, it will come out from the critical entry point and execute the critical section. So in that way, one by one, both can executing. So once P0 is executing, another P1 will execute, then P0 will not get the chance to execute. Then, P0 will execute, then P1 will execute, and then again P0 will execute, and then again P1 will execute. In that way, alternatively, both are executing the code, and both are, let's say if one is a producer, another is a consumer, if we'll have these type of code in the critical section, we have the buffer code and all those codes are there. Then this, if we'll apply this particular thing over there, then there will be the alternation between the producer and the consumer. If producer always want to produce and consumer always want to consume, then with this particular logic they can do it, right? Now why we are learning this? We are learning this to understand that for the process synchronization, for the process synchronization, we should have some condition that has to be satisfied. Or you can see that to use the critical section, we have some rules that has to be followed. Those rules are generally, we have in some book there is a 3 rule, and some other book there are 4 rules. So here we are going to learn 4 rules. These 4 rules has to be satisfied for the algorithm, which says that algorithm can be able to run for the cooperative processes. The cooperative processes always share something, either the variable or the memory or code sections or some sort of hardwares. So between them, we need some sort of synchronization, as well as these condition has to be satisfied. So these are the rules for getting the critical section, or you can say these are the rules by which we can preserve process synchronization. The first condition or the first rule is mutual exclusion. Mutual exclusion says that if one process is executing into the critical section, if one process is already there in the critical section, then no other process can execute in their critical section. So because we know that if we have, let's say this is the 2 process example, if we have n number of processes, each process has their critical section, and if we are using some sort of algorithm in which if one process is executing its critical section, other process is not going to allow to execute its own critical section, right? Now if we are doing that, then that is called mutual exclusion, and this condition has to be satisfied. So I think you understood. If one process is already there in the critical section, then no other process will be allowed to execute into their critical section. Now the second essential condition in this particular critical section problem is progress. Now what do you mean by progress? Progress is that if no process is executing in its critical section, and there exists some processes that wishes to enter their critical section, then the selection of the process that will enter the critical section next cannot be postponed indefinitely. It says that whatever process, if this critical section is empty, no process is there inside the critical section. So the process who want to execute the critical section, allow them. It is not like if you are making the entry condition such a way in which no process is allowing to use into the critical section. That should not be there. Another thing is there, if we have, let's say, some processes, and let's say P0 just now executed the critical section, and forcefully, my code is like that, it is forcefully saying that P1 execute into the critical section. That also not be there. If P1 don't want to execute the critical section, it is not forcefully allowed to do that. Means fixed alternation is violating progress. It means we do not need fixed alternation. Alternation should be there, but depend upon the willingness of the process. If a process want to execute, yeah, please allow them. If a process don't want to execute, don't force them. So that is called progress. So I hope you understood. If the critical section is empty, it means that no process is executing into the critical section, then the desired process who want to execute into the critical section, we have to allow. Second thing, if nobody is in the critical section, it is not we don't have to do forcefully allocating the critical section to a process who doesn't want to execute its critical section. So we have two things that we have to follow in the progress. We doesn't have to force any process to not get into the critical section or to get into the critical section. In both the cases, we doesn't have to force it. That is called progress. Now come to the third condition, which is called bounded wait. Bounded wait says that if a process want a critical section, then that process need not to wait for a longer period of time. Means if process 1 is willing to get into the critical section, so at a particular time bound, we have to allow P1 into the critical section. Getting it? That is called bounded wait or bounded waiting. So a bound must exist on the number of time that other process are allowed to enter their critical section after a process has made a request to enter its critical section and before that request is granted. It says that we first of all we have to restrict one process to get into the critical section again and again after another process has requested for the entry into the critical section. So if no process has requested for the critical section, you allow one process to go into this critical section again and again. But once another process is requesting to execute into the critical section, then this process need to be forcefully wait. Getting it? That is called bounded wait. Assume that each process execute at a non-zero speed. So we have to see that all the process has same speed, as well as no assumption concern relative speed of the processor. So processor also doesn't have the relative speed that if we have n number of processes available, so it is not like we have a different relative speed to these processes. So that thing we have to ignore while bound waiting. Now come to the next condition. It says that no assumption related to hardware in speed. So no assumption we have to take while giving any process into the critical section based on the hardware or based on the speed of the hardware. Now in these rules, these two rules are essential rule, and these two rules are optional rule. So we have some optional eligibility and we have some essential eligibility, right? So here the essential eligibility is mutual exclusion and progress. So whatever algorithm that we are saying is good for the critical section, we have to look for these two conditions need to be satisfied. If this condition is also satisfied, then well and good. And this condition is relatively satisfied because this is saying that we doesn't have to make any assumption related to the hardware and the speed. Okay. So mainly we have these three conditions. If these three conditions satisfy, this condition has also been satisfied. But you understood that this is the optional condition and this is some essential condition. So you make it a star like. So this is essential to be to give the solution for the critical section problem. So I think you understood these four conditions. In some book it is only three conditions because it is an understood problem. This problem is the understood problem, so we doesn't bothering about it. But mutual exclusion and progress we have to satisfy. If it is satisfied, we say that yeah, it is a good algorithm. And if bounded wait is also satisfied, then it is well and good. So it is all about your critical section and the critical section problem solving conditions, or you can say 4 different rules related to the critical section that need to be followed. So in the critical section handling, we may have two approaches, depend upon the kernel is preemptive or non-preemptive. If the kernel is preemptive, we allow preemption of the process when running into the kernel mode. And if the operating system that we are using is non-preemptive, then run until existing kernel mode blocks or voluntarily yield CPU, essentially free of race condition in kernel mode. So what it is saying that in the kernel mode, when we are using it and we are saying that it is non-preemptive scheduling, so one process will execute all its process. And if we are talking about preemptive, then if one condition, even it is executing into the critical section, will deallocate the CPU and will allocate another process into the CPU. So we may have two ways. So generally, this is a normal way where we can satisfy all the conditions related to critical section. But we are talking about preemption, right? So always we talk about preemption. Why we talk about preemption? It will increase my utilization of CPU, responsiveness. It will reduce the waiting time, all starvation problem, all those things can be removed here. Like an example of round robin, right? So ultimately we have to use preemptive scheduling. Non-preemptive scheduling is okay for the critical section, but not okay for the CPU utilization. So we have to look for that. So these conditions need to be satisfied all the time, right? So that we have to take care. Now in the next class, we'll see some more examples related to the critical section and this critical section problem. And we'll see some of the solutions related to that. And on that solution, we'll try to find out whether they are having the rules, essentials rule or not. What are the essential rule? Mutual exclusion and progress are the two essential rules that need to be satisfied for each and every algorithm, which says that it is for the critical section solution. So I think the concept is clear till now. So related